Okay, all right. Well, look at this. We got 12, 13 of you, 12 of us. Okay, so it's off schedule, so I'm happy. All right. Well, I'm happy you guys are here. I hope you had a good weekend, and I appreciate your flexibility. And those of you who are watching online, I'm glad you guys are watching online. And all right, well, let's take a look at today's topic. Well, so on Friday we left off, and I showed you this thing, and I said, well, maybe we'll talk a little bit more about it, and we will a little bit, okay? But let's get into today's lecture. Oh, you know what? I forgot. I need to set up the lecture view quiz. Hang on. Let's do that over on this screen over here. Lecture view quiz. How do I do this? Okay. Quiz week 3. Something happened. Okay, give me a second. I apologize. Okay. All right, sorry. Okay, just give me a second. I gotta get this. So I'll start my lecture, and then I'll be working on this lecture 3 view quiz business in a moment here. Okay, so today we're going to cover more regularization and the bias variance trade-off. I am recording, right? Yeah, okay, recording on this computer. Okay. All right, so quick review. Here are just some fill in the blanks. The regularized loss function combines the OLS loss function with blank. And then the blank term is used to determine which goal has greater priority. So just fill in these answers in your head, and let's see if you guys got the right answer, which is the regularized loss function combines the OLS loss function with a penalty for the complexity. And then the second part is the lambda term, or some constant, okay, is used to determine which goal has greater priority. So, all right, hang on. All right, I'm fixing this thing up because I messed this up. Okay, I think the week 3 Monday lecture review quiz is up. Okay, and I'll give you your answers shortly. Okay, all right, so back to what we are talking about. All right, so this is what we left off with. On Friday, we said we have LASSO, we have ridge regression, and all of these, we have the OLS term, which is this curly L, plus some penalty for complexity. All right, and so for LASSO, the penalty for complexity is the absolute value, the sum of absolute values of the vector of coefficients. And for ridge regression, it's the sum of the coefficients squared. So you take the coefficients, you square them, and that's the penalty for complexity. And so the size of the coefficients themselves actually play a role in how big the penalty is. So bigger coefficients mean more penalty, and we say, well, the side effect of that is you should always kind of standardize your variables and whatnot. So what size unit you use doesn't play a role, because otherwise you can always just change your unit size and shrink your coefficients, right? Because if you measured something in, say, millimeters, and you'd say for every millimeter, our expected weight goes up 1 gram, okay? So that's one coefficient. And if you say, well, I want to shrink that even more, you can, instead of millimeters, you can change it to kilometers. Or actually, it would just be the opposite, right? So, because if you go up 1 kilometer, maybe you would go up 1,000,000 grams or something. So if your measurement is originally in kilometers, you can change it so your measurement is in millimeters. And so instead of going up, you know, I don't know, 1,000,000 grams or something, it'll only go up 1 gram or something. So changing the units is, you know, it would be like a cheating way to work around. And so standardizing that eliminates that issue. Okay, there is another thing called ElasticNet, which is kind of a hybrid of LASSO and regression. So LASSO uses the sum of the absolute values, and then ridge regression is the sum of the squared values, okay? And so ElasticNet says, you know what, our complexity will be the absolute value penalty plus the squared terms penalty. And this one is alpha multiplied by alpha, and this one's multiplied by 1 minus alpha. So basically, if alpha is equal to 0, then it basically becomes ridge regression because you'll have no absolute value penalty, and the entire penalty will be based on the sum of squares. Okay, so if alpha is equal to 0, it's pretty much ridge regression. And on the other hand, if alpha is equal to 1, then this term becomes 0, and the ridge regression, the squared coefficients part goes to 0, and then it becomes basically LASSO. All right, so you'll have something between 0 and 1 for alpha, and it will be some kind of blend somewhere between LASSO and ridge regression. It's kind of, you can imagine some kind of knob where it's like, do you want to be more like ridge regression or more like LASSO? And that's pretty much what we have here. And that's ElasticNet. And this is implemented in R in this package called GLMNet. GLMNet implements ElasticNet, and yeah, we can do that. And so if you wanted to do LASSO, or if you wanted to ridge regression in R, there really isn't a package directly for LASSO alone or a package for ridge regression alone. You'd basically use the GLMNet ElasticNet package, and then you would either use alpha equal to 1 or alpha equal to 0 to get LASSO or ridge regression or something in between. Okay, so what's kind of the difference between LASSO and ridge regression? We talked a little bit about this on Friday, and we said, you know, I just drew you some pictures, and I said LASSO, you get the diamonds, ridge regression, you get the circles, and we saw the contour plots, and they were kind of a blend between the ellipses and the diamonds, or the ellipses and the circles. This is what the documentation for GLMNet says on the topic, and it says it is known that the ridge penalty shrinks the coefficients of correlated predictors towards each other, while the LASSO tends to pick one of them and discard the others. The ElasticNet penalty mixes the two. If predictors are correlated in groups and alpha equal to 0.5, tends to select the groups in or out together. This is a higher level parameter, and users might pick a value up front, else experiment with a few different values. Okay, and so it says the ridge penalty shrinks the coefficients of correlated predictors towards each other, and we saw that a little bit, right? We saw over here, as we were looking at ridge regression. Remember, this is the coefficient for x1, which is W1, and the coefficient for x2, which is W2. The optimal OLS is something like 1.5, okay? 1.5 for the coefficient for x1, 0.5 for the coefficient for x2, W2. And what we saw is, as we use ridge regression, the ridge regression parameters represented by this blue dot tends to go towards this line where W1 is equal to W2, okay? So rather than getting 1.5, which is the OLS term, we get something over here, we get something like 0.9 and 0.6, something where the coefficients W1 and W2 are closer to each other. It approaches this line where W1 is equal to W2. So the ridge regression kind of shrinks them together. And so, and then the other thing with LASSO, it says it tends to pick one and discard the others. Okay, and we see this as well as it's shrinking them. Okay, as it's shrinking the parameters, it shrinks them both until one of them becomes 0. All right, and this is basically Lasso picking a coefficient so that one of them is 0, and then the other one it has kind of kept. Okay, so this is kind of the idea that it picks one and discards the others. Okay. All right, and then ElasticNet says if you've got predictors that are correlated in groups, then alpha tends to select the groups in or out together. Okay, and it just says you can pick a value up front, or you can kind of do via trial and error. You can experiment and see things that, okay. Because the lasso does tend to push coefficients down to 0, it can be used as a way for variable selection. So if you want to reduce your model by strictly eliminating some of the variables, lasso can be a good choice. Okay, let me go ahead and give you your first view quiz answer for today, which is the letter A. A as an apple. A as an apple is your first view quiz answer. Okay. All right, and so if we wanted to use GLMNet, it might look something like this. You would call library GLMNet, and what you would need is, so this is the way it works is a little bit different from what we're accustomed to. You know, normally you'd call something like LM or GLM, and you do y tilde x and y tilde your x variables. Here you would have a matrix of matrix X, which is basically your predictor columns. So you're going to have a matrix X of predictors, and then you also have a matrix Y, basically a column output, column matrix of outcomes. Okay, and then the default settings of GLM is alpha equal to 1, which performs lasso, and then again as and then there's also a lambda parameter, which it kind of figures out on its own. But again, you can kind of crank alpha down to 0, so it turns into ridge regression, or you can set alpha equal to 0.5, and you get some kind of blend between the two. Okay, so here I'm making up some made up data. This we have 4 x variables. X1 and X2 are correlated, X3 and X4 are correlated. X1 is independent of X3 and X4, and X2 is also independent of X3 and X4. Okay, so X1 and X2 correlated, X3 and X4 correlated. And then as far as the Y variable goes, okay, Y is related to X1 and Y is related to X3. Okay, the coefficient for X1 is, the true value is 3, and the coefficient for X3 is negative 1.8. Okay, now X2 and X4 are correlated to X1 and X3, but there's actually no relationship between Y and X1, or Y and X2 and Y and X4. Okay, so Y depend only on X1 and X3, but X1 and X2 are correlated, X3 and X4 are correlated. So if you look at the data, and and you say, is there correlation between Y and X2? There will be correlation. If is there correlation between Y and X4? There is correlation. But as far as the true values, it's only dependent on X1 and X3. Okay, I add some random noise, and we get our Y values. And so we're going to do GLMNet, and we fit X and Y. We do our fit there. This is lasso. Okay, this is lasso with alpha equal to 1. And it spits out a whole bunch of stuff. Okay, this is kind of the default output of GLMNet, and it's a little bit hard to read. Okay, this is DF0, DF1, DF2, percent deviation, and it starts off at 0, and it goes up to like 10, 20, 27, 34, 35, up to 79, 81. And then the lambda starts off at 3, and it gets smaller and smaller and smaller. Okay, so what's going on? Okay, so we have a total of 3 columns. Okay, the first column is a degrees of freedom. Okay, it's the degrees of freedom spent on this model versus the empty model, which is basically how many additional parameters, how many parameters or the number of variables are being used in the model, okay? So if we have df0, this means 0 additional parameters or 0 additional variables are used. And so, and if you don't use any variables, you're not going to be able to explain any of the variation, right? So this second column, the percent of deviation explained, is the sum of squares regression divided by the sum of squares total. And so the sum of squares total is basically your total variance times n minus 1. And if you're not using any variables, of course, you're not going to be able to explain anything here, okay? And then as soon as you include one of the variables, you're going to be able to explain some of the variation, okay? So df1 just means we're including one variable only, but remember with LASSO, we shrink that coefficient. So if we include one of the variables, but shrink the coefficient, it's only able to explain 10.99%. As we allow it to get bigger and bigger, we can explain a little bit more of the sum of squares total, okay? And basically, the relationship is as we decrease lambda, okay, which is kind of automatically determined by GLMnet, as we decrease it, it allows for the coefficients to get bigger, and it allows for more and more of these coefficients to not be 0, okay? So it's kind of, as we're decreasing the lambda. So here that my lambdas are just on a completely different scale, but as I decrease the lambda, they become closer to OLS. And as I increase the lambda, it kind of pushes, it shrinks the coefficients until one of the coefficients effectively becomes 0, right? So this is a different example. Here, there's only 2 coefficients, W1 and W2. Whereas over here, we could technically have up to 4 coefficients because we have 4 x variables. But using only just kind of 2 additional degrees of freedom, or having 2 additional coefficients, we're able to explain an increasing amount of the variation, okay, by kind of decreasing the lambda. So by looking at this, you kind of want to just kind of ballpark a sweet spot where you say, okay, how much variation am I able to explain? And it looks like we can get 90%-ish or something by having 2 additional degrees of freedom and having a lambda of 0.62. And maybe if you want even more deviation, you can shrink your lambda even further. And we got something like that, okay? So basically, so when lambda is large, the model complexity is punished greatly, and this pushes all the coefficients to 0, and we have basically df equal to 0. As lambda decreases, models are punished less for the complexity, and this allows the models to incorporate more terms. And if lambda reaches 0, then there's no penalty for complexity, and basically you get the OLS model coefficients. So if lambda becomes 0 here, then you get just whatever OLS would have spit out. Okay. All right, so just for kind of model comparison, here is if we just fit an OLS model, and using just plain old linear LM, R figures out that that the X1 and X3 terms are significant, X2 and X4 are not significant, which is according to which is the case that we have for when we generated the data. When we generated the data, Y was dependent only on X1 and X3, had nothing to do with X2 and X4, and R figures that out using LM. And the R squared, multiple R squared, is 0.954, okay? And we can see that as I shrink my lambda, and it kind of gets cut off, we get something closer, it gets higher, but we don't ever exceed that 95.4% R squared value, because when lambda equals 0, it's going to reach OLS. So we're not going to outperform OLS. Okay. All right. So this is what we have, and here's also kind of a picture of how much of the we're able to explain. So the deviation ratio at 0, when lambda equals 0, we got 95.4%, 0.954, which is this multiple r squared here. And as lambda increases, the amount we can explain drops, and then until, and there's kind of this tiny little bump here, okay? And that's kind of when we go from, we have a change in the degrees of freedom. So when right around at 2 point something, okay, we go from having 2 degrees of freedom down to 1 degree of freedom. And so there's kind of a further shift here, okay? And so you can kind of say, well, I don't know what lambda we should pick for this, okay? If you want to see what the actual coefficients are for x1 and x3, or even x2 and x4, they just don't ever show up with LASSO, then you can fill out the, you can ask for the matrix, okay? And you can call $sign beta, and this will give you all of the coefficients. It comes out as a sparse matrix, which basically, if it's 0, it just doesn't fill anything in. So if I say print sparse matrix on the beta, this is what we get, right? And so this first column, this S0 column, corresponds to having 0 zeros for all the coefficients. The next column is, what is the coefficient for the for fit S1, which says we got 1 coefficient, 1 degree of freedom, and we're able to explain 10.99%. That's using this term, okay? And as it gets bigger and bigger, we're able to explain more. And then at S4, we now have 2 coefficients. So, okay, so at the 4th model that we fit, this I guess the 5th model, because it starts off at 0, 0, 1, 2, 3, 4. We have 2 coefficients, and we're now able to explain 35.19%, and that's what we have. And as we keep going, the coefficients get larger and larger. Okay, if you do as dot matrix rather than the dots, it puts in zeros. Okay, which I don't know feels more or less comfortable for you regarding the output of GLMNet. Okay, and if you go all the way to the tail end of the matrix, if you go all the way to the tail end of the matrix, then you will get basically something that approaches the OLS coefficients, okay? You don't get all the way the OLS coefficients because the GLMNet always applies just the tiniest bit of lambda, but you can see if there's basically a minimal amount of penalty applied, then the coefficient is 3.016, a 0, negative 1.78, versus the OLS coefficients are 3.04 and negative 1.84. Okay, so something very close to over here, we have some very close to the OLS coefficients. Right, if you want, you can say, I want, what are the coefficients associated with a particular lambda? Okay, and so you can set S equal to 0.2 or S equal to 0.1 or something. And as your lambdas get bigger, the coefficients get closer to 0. Okay, so for 0.2, we have 2.83 and negative 1.63. And as the lambda here specified by the argument S is equal to 1, a larger value of lambda, it pushes those closer to 0. So we have 2.03 and negative 1.95. Okay. How do we pick what lambda we should use? Okay. What regularization term we should use. And so I don't know if you can see this picture. Let me zoom in a little bit. Okay. So GLMNet can kind of do its own cross-validation and give you an estimate of what it thinks you should use. Okay. All right. And so GLMNet, so if you call cv.glmnet, this will do cross-validation on GLMNet, and it'll automatically kind of do the training and test or train validation splits and kind of fit a bunch of models using different values of lambda. And this plot, if you do plot of the CV fit, okay, what we'll see is that when the log of lambda, Okay, so for whatever reason, they use the log of lambda rather than the lambda itself. When the log of lambda is 1, which is basically lambda equal to wait, 0. Wait, hold on. Log of lambda is equal. Yeah, wait. No. What? Hold on. I'm confusing myself here. Okay, so when lambda is big, okay. So okay, lambda is 3. Okay, so log of lambda. Okay, I'm sorry. Lambda, when log of lambda equals 1, it means lambda is equal to e. And then here, the original lambda on the brain here. So the first lambda the max lambda we have is 3.02, which is just a little bit over e, right? Okay, so it's a little bit over 1, and then the next value was something, and so we basically have a lot of kind of mean squared error here. And as we increase it, we can see the mean squared error shrink, and it kind of gives you this kind of these lines here, okay? And so what we can do is we can ask, what is the value of lambda that gave us the smallest amount of error, okay? The cross-validation. The smallest amount of cross-validation was at lambda equal to 0.05, which I guess the log of 0.05 is something around -3. Is that right? Now I want to just double check my own thing. Okay, so 0.05 ln. Okay, yeah, -3. So right around here, this is the value of lambda that minimized the cross-validation error. Okay, and then you'll notice it includes just a tiniest bit of like error terms. There's like a little confidence interval around this thing. So this is the value of lambda that minimized the cross-validation error. And there's also, because there's some randomness associated, it gives it a little bit of an error term. And so this dotted line over here corresponds to what? -1.3, 1.25, something around there. Okay. And this dot is a little bit higher than this red dot, but it's within the confidence interval. Okay, so this is like within, so I guess statistically speaking, this amount of error is not very different from this amount of error. And so kind of the wisdom, if you don't want to do any kind of additional thinking, is that pick the biggest value of lambda so that you're still within the error term of the smallest value, the one that minimized the cross-validation error. Okay, so the one that minimized the cross-validation error is something right around 0.05, which corresponds to log of -3. And then if you want something bigger than that, which is still within, the error term, you can go up to, whatever value that is, which is something else, okay? So that's lambda.1 SE, okay? So you can ask for the largest value of lambda that is still within one standard error. That's kind of the error term of the minimum lambda, okay? So the minimum lambda that resulted in the minimum cross-validation was 0.05. The lambda that still produced amount of error that was within one standard error of the minimum lambda is 0.268. So this might be kind of your recommended, the autopilot recommendation. So if you don't want to have to do further thinking, this is usually an okay number to use as far as what lambda should I use, right? Because what lambda should I use is always a little bit of a tricky thing. And we always say, well, use some cross-validation. And GLMNet will kind of do a lot of this stuff automatically for you. Okay, does that kind of make sense? All of this stuff I've been kind of talking through. Let me go ahead and give you your second view quiz answer today, which is the letter B. B as in bear is your second view quiz answer. B as in bear. Okay, I think this is everything that I just explained, but I'll go ahead and read through it really quickly. Okay, so the lambda.min is the value of lambda that produced the smallest cross-validation mean squared error. This cross-validation mean squared error has a standard error because it's subject to the random train test splits. Therefore, the smallest cross-validation error may not be significantly different from another cross-validation error that is slightly larger. The lambda.1se is a larger value of lambda that still produced a fairly small cross-validation mean squared error. It didn't produce the smallest cross-validation mean squared error, but it produced a cross-validation MSE that was still within one standard error of the minimum cross-validation MSE. Okay, so this is often the lambda that's we recommend. Okay, so why even bother all of this? So this is kind of the question, you know, benefits of regularization. Why bother with all of this stuff? Why shrink down your coefficients for no good reason? Okay. So here's the thing. When you fit a model to some observed data, the coefficients that we're estimating are subject to just the random noise in the observed data, right? Anytime somebody takes a random sample of data, there's randomness there because it's a random set of data. Someone else could grab another random sample and their values will also be slightly different. And if both of you fit OLS models, this person's coefficients will be different from the other person's coefficients, right? So OLS, you guys talk about this, the BLUE, the best linear unbiased estimator, right? And that means in the long run, the coefficients are unbiased, okay? Meaning that if you repeated this process 1,000,000 times, getting random samples and fitting OLS, then the expected value of each coefficient, you know, your slope, your intercept, whatever other coefficients you have, all of those, the expected values will be the true values in the population, okay? And among those, the OLS have the best estimates in that they have the lowest amount of variance among all unbiased estimators that are possible, okay? But we have known issues, and that is if certain variables are highly correlated, the coefficients of these variables exhibit high variance, right? In that, so if you're doing like a survey of properties and you have variables that are highly correlated, such as square footage of the house and the number of bedrooms and a lot of these things, you know, some models might say the coefficient applied to the square footage should be quite big, and then other models might say this coefficient for the number of bedrooms should be quite big or something like that, okay? And because those things are highly correlated, and depending on the random sample you get, you can get quite a bit of variance as far as what coefficients you get. And so what regularization does is it reduces the variance in the fitted models. It reduces the amount of variance you have for those coefficients, for the slope parameters and stuff. It says, okay, let's try to shrink the amount of variation so that if two people take random samples and they both fit regularized models, like if this person fits a ridge regression and this person fits ridge regression, their coefficients won't be exactly the same, but the amount of variance between their coefficients won't be wildly different, which could happen with OLS, right? So two people fit OLS models, their slope parameters could be quite different. If two people fit ridge regression models, even if they have different random samples, their ridge regression coefficients won't be super different, slightly different, but not as much, okay? So we're reducing the amount of variation in those estimates, but the issue is we're introducing bias. We're introducing bias in that in the long run, the expected values of these things aren't the same as the true values, okay? So in the long run, after fitting many random sets of data, LASSO or ridge regression coefficients will have an expected value that's not equal to the true coefficients that exist in the population, okay? But the benefit is that the variance in these estimates, the variance of these coefficients is smaller, okay? Lower variance is a good thing, okay? Having less variance in the coefficients is a desirable trait. And what that means is that the model estimates are less likely to be swayed by kind of just the noise that happens in the observed data, meaning that you don't have to worry as much that your coefficients are picking up a bunch of noise that exists in this data set, right? So if the population exhibits a lot of noise, and you're concerned that that your OLS coefficients are wrong because of just random sampling, using regularization can reduce that, right? And so that's what this diagram is supposed to be. Okay, so this is, we have generated different random samples. It's like 1,000 different people took random samples from the population. The population, the true values in the population have parameters 1.5 and 0.5. Okay, but because of the random samples are random and subject to random noise, a lot of people, when they took a random sample, they got coefficients around 1.5.5. But some people, because of just randomness, their coefficient estimates are like 2.00. And some people, just because of randomness, their coefficient estimates are 1.0, 1.0. Okay, most of the time it's something around 1.5, 0.5, but it's there's quite a bit of variance as far as the different parameters go. When you do ridge regression, it shrinks the amount of variance. Okay, so this is ridge regression with a small lambda. The amount of variation is represented with this red cloud. Okay, so still subject to random noise. Okay, some people get ones that are off and stuff, and you can see the center of this red cloud is not 1.5.5. The center of the cloud is over here, but we have less variation. Okay, and as we increase the lambda, okay, again, now the center of this cloud is way different from 1.5.5. It's like 0.75.6 or something. It's quite different. Okay, but the amount of variation is quite a bit smaller, right? So 2 people can take or 1,000 people can take different random samples, and they'll have slightly different estimates, but the amount of variation from one person's coefficients to another person's coefficient is a lot less. Okay, whereas over here, there's quite a bit of variation as far as what somebody's W1 and someone else's W1 parameter estimates are. Does this picture make a little bit of sense of what I'm trying to explain? I hope, maybe. There's only a few of you here with your cameras on, so I'm looking at you guys. And everybody else who's watching on YouTube or a video, I hope it makes sense. And I'm just not able to see your facial reactions as far as whether it makes sense or not. Okay, so if okay, so what was I saying? If the coefficients of a model change drastically with each random sample, then you might not be very confident in your current set of coefficient estimates, right? You might think, well, maybe my slope is too high or too low by a lot. Okay, on the other hand, if the coefficients of a model change very little with different random samples, you can have a little bit more confidence in your current set of coefficient estimates. Okay, so that's kind of what we're going through here. I do another kind of simulation study where I'm just generating a whole bunch of random samples fitting OLS, LASSO, and ridge. So the true relationship is 3 and -1.8 on X1 and X3, and I generate a bunch of random noise. Okay, and I do this a bunch of different times. And we're going to go ahead and just use LASSO and ridge regression, and I'm going to just use GLMNet to select the 1SE lambda. Okay, we're just going to pick the largest lambda that's still within 1 standard error of the minimum lambda. Okay, and we're going to store all of the coefficients. And so this is just the code that I run to do all of this. And here are the plots that I'm producing. Okay, so as far as the X1 coefficient goes, okay, we can see the true value was 3, and OLS, so this represents, so what we're looking at here is the distribution of X1 coefficients. Okay, the true value is 3, and sometimes we get coefficients that are higher than 3, 3.5. Sometimes we get coefficients that are less than 3, 2.5. So this is what happens with OLS. And in the long run, they are unbiased. It's centered around 3. Okay. With LASSO, we get coefficients that are shifted down smaller. It's centered around 2.65, 2.7. Okay, sometimes a little higher, sometimes a little bit less. Okay, and it seems like, well, that doesn't really look like it's reducing the variance here. Okay, and I would say, yeah, it's probably not reducing the variance that much. Okay, and ridge regression, they're centered quite a bit different, centered around 2.25, 2.3, something around there. The variance, okay, from the center to the high going up to 2.8, to the low 2 point, so we're going up around 0.5 and down 0.5. And so I would say, okay, we reduced the variance just a touch here. Okay. So if I look at for OLS, the mean is 2.997, the true value is 3, and the variance is 0.063. Okay. And for LASSO, okay, the mean is 2.68. I guess the variance has gone down, 2.033. Over here, the mean is 2.26, and the variance didn't print out, but it's smaller, okay? You'll just have to take my word for it, it's smaller. Okay, this is where we start to see a little bit more of an effect here, okay? For x2, remember the true relationship between x2 and y is that there is no relationship between x2 and y. So the true coefficient is 0. But when you do OLS, just because of randomness, sometimes, a lot of times it gets something around 0, but sometimes it gets something as low as -1. Sometimes it gets something as high as 0.5. Okay, and that's just because of randomness. Sometimes it picks up some kind of relationship between y and x2, even though there actually is no relationship between y and x2. Okay, when you look at LASSO, this bar, it looks like it's centered at -0.1, but it's centered at 0. Okay, it's centered at 0. We just have a whole bunch of times where it just said it's 0. LASSO kind of pushed this down to 0. And then on rare occasion, it said, okay, I'm estimating 0.1 or 0.2 or something around there. Okay, so so here we get something right around 0. With ridge, it doesn't, because it penalizes a squared thing, it says, you know what, it's not even worth going down to 0. Like, just leave it at 0.2 or 0.4, because when you square it, it gets really small, right? So with ridge regression, it says, I'm estimating the coefficient to be 0.5, because 0.5 squared is only 0.25. That's hardly a penalty. So ridge regression gets a little bit off. And then if you look at the amount of variance, the OLS has a variance of around 0.087. Okay, the true value is something around 0, variance of 0.087. Whereas for LASSO, okay, all of these things got cut off here. For LASSO, the variance is very close to 0, very little variance. Okay, and the mean is pretty low as well. Okay, and then over here, the variance here is not as small as as LASSO, but it's a little bit smaller than 0.087 there. Okay, and then I can kind of go through. All right, and I guess that's it for the X2. And I think in your next homework, so I just posted homework 2. I know you just submitted homework 1, and as soon as you submit homework 1, I come at you with homework 2. But homework 2 is posted, and I have you follow some code, and it produces these plots, and I ask you to talk about this. But just maybe you can just rewatch this part of the lecture to listen to hear what I said. Okay, let me talk a little bit about the bias variance trade-off. This is something we got just a few more minutes to cover this, and this is just kind of a little high-level overview. And the idea here is that the expected prediction error is when you make a prediction for a point that you haven't seen, how much error can you expect there to be? Okay, and there's a combination. It's a combination of a few terms. It's a combination of the amount of bias, okay, and the amount of variance, and the amount of kind of just inherent error or variation that exists in the data. Okay, so the bias is how much bias is there between the expected value of your estimates and the true parameter estimates. And then the variance is kind of how much variance is there from one set of estimates to another set of estimates because of just different randomness. And then finally, there's just random noise inherent to the system. So all of these things kind of add together. Now, here are the definitions, okay? Expected prediction error is the total squared error between the actual values and the fitted values for a new data set, okay? The expected value, the total error would be the true relationship plus the random error minus the fitted values, okay? The bias is the expected difference between the predicted value and the actual value. And the variance is the variance of the predicted values. I'm sorry, these are about the predicted values, not just the coefficients, okay? And sigma is the standard deviation and the noise in the generated data. So I introduce a little bit something called LASSO regression. And we don't really cover this, but basically it's this concept of local regression. And it's this idea of you just do some linear regression models and you average a bunch of linear regression models within kind of like a window. It's a little bit like, I don't know if like in finance, there's kind of this idea of like a 7-day moving average. It's a little bit like that, except it's not just the moving average, it's like a moving linear regression. So it's like the linear regression applied to like this window of 7 days, and the linear regression applied to this window of 7 days, and or X number of data points that you have. Okay, so the true relationship is going to be defined, is going to be a quadratic relationship, but I'm going to add noise. I'm going to add noise. Okay, so this is the true relationship, it's quadratic. Okay, but we add noise, and what we're going to do is I'm going to just say, all right, let's take a look at some values spaced out here, and I'm going to start by fitting a straight line. Okay, so can you see these light gray points? Okay, so the true relationship is the dotted red line, and I hope you can see these light gray points. All right, and so these are just because of random noise, the data that we observe is this, and I say, okay, now fit a straight line to these light gray points, and we get this. I should have been doing this whole time. Okay. All right, so this is not a great model. It's a straight line. It should have been a quadratic one. Okay, but here is here's another set of random points. Okay, again, the generating model is the dotted line, but it generates these purple dots, and we say fit a straight line to the purple dots. Okay, and then here's another set. Again, these dots, the data that we've observed, are generated by the dotted line. Okay, but we say just fit a straight line to the orange dots. Okay, and so if I compare those three lines that we've looked at, the blue, the purple line, and the orange line, okay, we get slightly different estimates. Right, so these aren't great models, but how much do these blue, orange, and purple lines vary from each other? They don't vary that much. Okay, they don't vary that much. They're quite similar. So this would be something where we have high bias in that the model does a bad job of doing the actual relationship, but the amount of variance, low variance between the models that we fit, in that the blue, purple, and orange lines don't have much variance between them. Okay. On the other hand, I have an overfitting model. Okay. So I don't know if you guys can see, I should have picked different colors, but the light gray dots are all over the place. And this is a model that fits those light gray dots very, very closely. Okay. This is a local regression, and I used this parameter that says fit them as close as you can. So it fits these dots really, really well. Okay. And then I say, well, generate some new random dots in purple, and it fits these purple dots, and we say fit the line very, very closely. And I say do this in orange also. And so here it does that. Okay. And so what do we end up getting? Okay, if we look at the three lines, those three lines vary wildly from each other. Okay, so if you look at this spot right here, orange is way down here, blue and purple are way up there. If you look over here, blue is way up here, and orange and purple are down here. There's a lot of variance between these different lines. But we can also see each of these lines kind of hug this dotted red line fairly well. I'm going over my time a little bit. How many view quiz answers have I given you? 2. Okay. Your third view quiz answer today is B. B as in bear. The third one is B. B as in bear. B as in bear is your third view quiz answer. Okay. So this is kind of the idea that we're going for, is just that if you fit a bunch of these things, the average will be close to the dotted red line. But when you look at each individual line, the individual lines vary quite a bit from each other. Okay, so you have low bias in that the average of these things is kind of close to the red line, but high variance in that one model differs quite a bit from another model. Okay, so I'm going to just repeat this a whole bunch of times, and you get these kind of these super colorful graphs. Okay, and so what happened here is the true line is the quadratic line in black, and I fit a whole bunch. I said generate some random data, and for each of the random data, fit a straight line. Okay, and so what we see is we get like Mario Kart Rainbow Road here, but it just, all of these lines are quite similar to each other. It's supposed to be low variance, okay, but high bias in that if I average all of these things, these white dots represent the average of all of these lines, and we can see, okay, these dots are way off. Okay, over here, we get, rainbow spaghetti here, and the lines are way different from each other, But if you average, the points, we get something, and it kind of, they're not exactly on the black line. Okay, so the average of all of these points right here is this white dot, so it's a little bit off, and the average of all of these points are right here, but overall, okay, the average is quite close to the true line. Okay, but if you say, well, how much variation is there from line to line? There's a ton of variation, right? So this is low bias, high variance. So maybe not that desirable, and so you want something in between, where you can adjust some parameters. So maybe not too very low bias and not too much variance, and that's kind of the goal that we want. And I have some paragraph of text explaining kind of this, but it's all kind of the idea is that we want something in between where we don't have a ton of variance from one model to another just because of random noise. Okay, but we also don't want to have this where if we have very little variance from one random model to another, but the average of all of these things is no good. So we have high bias, low variance, low bias, but high variance. We want something in between, and that's kind of this bias variance trade-off here. All right, that's it for today. I will have office hours, I guess. I realized though, like you already turned in your homework, so maybe nobody will come to office hours, but I'll stick around, and I'll hold office hours for the next hour unless no one's here, and then but that's it. Thank you. I appreciate your flexibility in coming to class tonight, and we will see you on Wednesday. So see you then.